All right, so we're looking at less than 1.3, continuity and behavior, and limits. We will skip this 5-minute check since we went over the homework, and we should be all good. So we're going to look at limits to determine the continuity of a function and apply the intermediate value theorem to continuous functions, and use limits to describe end behavior of functions. All right, so we have our vocabulary that we'll learn throughout the lesson. All right, so we're going to look at limits first. So we have the definition here. We're going to use limits are kind of at like the direction that it's going, where it's approaching. So this, we have y equals f of x. So as we're looking here, as x is approaching the value of c, we're approaching that point. So in either direction, our x values are approaching whatever this constant is from either side. And then we have our vertical limit as well. So as our f of x is approaching in either direction, we're approaching that value L. So in symbols, we have the limit of f of x equals L. So the limit as x is approaching c, f of x equals L, which is red, just as I said. Questions? So we have 3 different types of discontinuity that we're going to look at, and this is where we have a break in the graph. So we have, just like that homework question, we have our rational here where we're approaching from this side and this side. This is an infinite discontinuity at x equals c, or the c value down there. If the function value increases or decreases indefinitely and x approaches c from the left or right and right. And then we have jump discontinuity, and this is like with piecewise functions where you have, it'll start or end at one point and then pick up at a different location. So here we have discontinuity here. So we're approaching c here, but then as we move up here, we're approaching the value of c at a different location. And then we have a removal discontinuity, and this is where we have in this case, a linear function, except we have a hole right at that one spot. So everything's all good until we're at the value c. So as we're approaching from the left and approaching from the right, we're approaching that value of c. But for whatever reason, due to how the function is set up at c, it just doesn't work. And so we have a nice little hole there. Questions? All right, so we're going to look at the continuity test. So there's 2 steps and then a check. So a function f of x is continuous at x equals c if it satisfies the following conditions. F of x is defined at c, that is, it actually exists. So when you plug in your value of c, everything is okay. And then you need to check if this works. Check to see does f of x approaches the same value from either side of c. So does the limit exist? Are you approaching, the same number? It is possible for the limit to not exist. All right, so then if both of those check out, the value that f of x approaches from either side of c is f of c. So does the limit as x approaches c equal that same value? All right. So it's kind of like checking these out and then doing the calculations for this, and then comparing to see if everything works out. All right, so let's do an example. So we're going to determine whether f of x equals 1 over 2x plus 1. To see if it's continuous at x equals 1/2, justify using the continuity test. So the first thing, did you guys write down the steps? Do you want to write those down? So our first thing we're going to do is we're going to plug in 1/2 into our equation, into our f of x. So now we're just going to evaluate. So we have 2 times 1/2 is 1 plus 1. So our f of c equals 1/2. So our f of 1/2. Now what we need to do is we need to test our limits. So we're going to make a little table. We have our C function here, which is 1/2. Now 1/2, I'm going to write it as a decimal because we're going to go a little bit to the left and a little bit to the right. So here, something a little bit bigger than 1/2 is 0.01, 0.5001. Now we're going to plug these into our original function. This is where using a table on Desmos is going to help immensely because you're going to enter the function once and then you can enter the values in. Alright, so as we are getting closer to 0.5, we have from this direction, we're approaching 0.5, and then from the left direction, we're approaching 0.5. So our limit, as x approaches 0.5, our limit of f of 1/2 is 0.5. All right, so we've done the first step by evaluating. We've done our second step by finding our limit. So now our last step is to compare. Does our limit equal the value when we evaluated? Does our limit of f of 1/2, does that equal what we evaluated it to be? Yes. So is it continuous at that point? In this case, this is a continuous function. And if we were to graph it, there wouldn't be any, it would just be like a nice smooth curve at 1.5. I always forget when it has everything there. So here they have the graph. So at 1/2, it's a nice smooth curve. We have it's not discontinuous at that point. Now looking at this graph, is it discontinuous at other points? Yes, but at 1/2 it's continuous.